of game theory, mechanism design, and machine learning. And in that vein, he'll talk about federated learning with strategic participants. Over to you.
Thanks very much, and thanks to the organizers for inviting me. So I'll be talking about, am I audible? Yeah, the last row, okay. So I'll be talking about federated learning. It's a little detour from the mainstream federation thing. So I'll actually, if you don't know what federated learning is, I have a few slides to explain that. So let's get started. So what is federated learning? So let's take this very simple example that there are 4 hospitals, and all of them have some data, not the same data, but divided into these 4 hospitals. And they individually want to learn a good model. So they want to learn the model of a disease. And each of these hospitals have some data set, DI, which are possibly non-overlapping. And how can they actually cooperatively learn this model? That is the whole idea. So the classical federated learning model assumes that all of these individuals, the agents, so in this example, I'll be using these hospitals as the agents. And there is some center who is like a mechanism designer who is trying to learn the model. And these agents, each of them having this data DI, and for notational purposes, we'll be using the cardinality of DI as SI max. That's the maximum amount of data that they can use. And they are somehow trying to cooperatively learning a specific model. If everybody could actually pull their data and whatever they could have learned, that is the final objective of federated learning. Just to give you a context that the type of the language models that you use while you are typing on Google keyboard is essentially a federated learning model. As you keep on typing, maybe you have observed it, as you keep on typing, your suggestions also get better because it is actually learning or fine-tuning a pre-trained model. And that's how the federated learning model works. How does it work? So let's say the classical federated learning models, the center starts with some model parameters, which might be very, very much off, let's say W0, and it is initialized randomly. Then it is sent back. So in the previous slide, this the center sends back all these model parameters to each of these individuals. Now, each individual has their own data, DI, and we compute something, let's say there is a common loss function on their own data set. They calculate the gradient with respect to that W and evaluate that on the current W0, which has been sent by the center. And they do not send back any data. That's not allowed in federated learning because of data privacy. You can only send back some learned information, for instance, the gradient in this case. So you can only send back that gradient, and center then calculates something like a weighted average, weighted in terms of how much data that they have, proportional to the data that they have. And this keeps on, then the center is actually updating. So you can see this step is something like a gradient descent step, one gradient descent step with a learning rate of lambda. So this is getting updated, and this is and the process keeps on happening over and over again. And because we are taking the summation, the average, this algorithm is known as the Fed averaging algorithm. It's a very popular algorithm for federated learning. Now, the fundamental NI is the size of DI. Yeah. Should have used SI max, but yeah. So NI is the contribution that agent I is making. Proportional, if someone has a lot of data, then their contribution will also be averaged in the proportional way. Okay, so one of the fundamental assumptions of this Fed averaging algorithm is that all the agents are truthfully contributing their entire data. So our learning, or federated learning, will be best if everyone's language models are given to the maximum possible extent, whatever data they have. If they can train on the entire data and then back those learned those gradients, then that will be the ideal thing, and that is already assumed in federated learning. what if some agent who has very little data, let's say one of these hospitals is a small hospital and it does not have enough data, and therefore the type of, so it may say that I don't have any data, but I still participate in the federated learning process. I learn a very nice model, but completely free. And then you see that there is no reason for the bigger hospital, which has a lot of data, to train the model on their data set. And this problem is called the free riding problem. And there have been works on first identifying and showing how bad this free riding can potentially be. Now, we actually need a mechanism. So in order to stop this from happening, we need a mechanism such that this kind of a thing does not happen. All the agents, irrespective of how much data they have, they should be contributing as much as possible. So that's the overall goal of this talk. So let us now move to a strategic setup where we are treating each of these agents as strategic agents. They have their own incentives to maximize. Now, the first assumption that we will make, because it is easy to handle, is that the data is unimodal. Everybody is sampling from the same data. So for instance, in the hospital example, every hospital is operating in the same region. So the disease distribution, everything is similar. It's just a matter that how many samples of this data that they can sample from this population. So that data distribution is unimodal. I'll make a comment regarding the multimodal distribution later. So therefore, the player set is 1 to n, and each agent has this private access to this data set DI. Imagine that this DI is the patients that go to hospital I. And therefore, those hospitals only can access their medical files and have that information. Now, strategies that, you can imagine that this sampling data is costly. So therefore, whenever we are deciding, an agent is deciding that I should sample this many amount of data, so let's say SI, which is a real number between 0 to SI max, that comes at a cost. So therefore, that picking what SI agent I should pick is a strategy of that agent. And once everybody chooses, this is the strategy vector, which will actually determine how good our model is. So what model the federated learning model is learning. Okay, so now we are actually trying to learn this model parameter of W, and we are going to represent or model its impact on a specific agent with this type of utility model. This is not something that we have come up with, but it has a similarity, and it is one of the works by Bhaskar and his co-authors. So the utility is a kind of a quasi-linear model which has two aspects. The first aspect is the benefit that you get, which is denoted by this function AI, which is a function of what model parameter you have learned and how much people have contributed. A stands for the entire S vector. Not only your contribution, everyone else's contribution. While the second part, the cost is only personal, because if I'm sampling SI amount of data from this population, that means that when patients come to my hospital, I decide how many tests to do for them. Let's say I want to measure their blood pressure or blood sugar. Each of these has some cost, so the cost is only personal, and it depends on how many number of samples you are sampling, how many number of data you are sampling. Now this. Yes, question.
AI depend on S given W.
So yes, good question. So we can actually think about the other model also. So where you can consider the whole thing as one. So W is a function of S. Of course, when you are learning some W, it's implicitly a function of S as well. So you can make that directly and consider AI as directly a function of S. That is already being done. So we are actually trying one step more. So this is more difficult to handle, and the other one is already known. So the results are already known. So yeah, so to give a quick example is that maybe you have a loss function which is dependent on W, but now if you are sampling more and more, your loss is possibly going down. So it is, in general, loosely speaking, is a function of both W and S. And that actually makes the problem harder because now we have to show convergence. So as we'll quickly come, is actually stepping a little ahead of time. But this is actually difficult to handle in terms of convergence guarantees and so on. Yeah, any other questions? Feel free to stop me if anything is unclear.
Of accuracy with
We'll come to that. All those assumptions will come to that. Yeah, so not directly, but yeah, something similar is required. Even some assumption is required also on the cost function. Okay, so we have already explained what accuracy and cost is. Let me move ahead. The question that we'll be asking here is, if we have this kind of a model, the utilities, because the agents are now completely strategic, they want to maximize their utilities. What type of equilibrium we reach? So in the Nash equilibrium, how much people contribute? And what should we learn from the center's perspective? What do we learn in the federated learning model? So these two things are important. And let us see one example where we are not actually learning very nicely. That is the classic assumption of federated learning where everybody will be contributing all their data is no longer true. So let's
point that so teacher jump looking at equilibrium, I guess truthful mechanisms are rolled out.
Yeah, so this is not exactly a truthful in the classical truthfulness scenario. We are just pushing everyone to contribute as much as possible. It's essentially a game theoretic guarantee that we want to give. Yeah. Yeah, so this example is actually showing that if suppose there are two players, two hospitals, let's say, one has a large amount of data, 990 data, so their S max is 990 and the other agent is very small, 9. And let's say for the accuracy function, pick something. This particular example is not dependent on W, but you can also create an example with W, and we will come back to this kind of an example later on. So in this case, so you can trust the calculations. The point is that if everyone is contributing the full data, you can see that the utilities are very low for certain agents. The people, the agent who, because we have assumed that there is the cost of sampling the data, if agent 1 who has a large amount of data contributes with all its data, then the cost is so high that their utilities are going negative. And for the other agent also, utility is reasonable, but you'll soon see, and one can do a calculation of Nash equilibrium to show that significantly less is actually being contributed. And in Nash equilibrium, the second agent will try to free ride. It will not contribute any data because it knows that I anyway learn something out of this system because the other agent is contributing some, if not all, at least half of its data. Okay, so this happens to be a Nash equilibrium, and that's not nice. So this essentially is known as free riding. One of the agents is actually not contributing anything, and it's trying to learn from the other agent's data. So how can we actually stop this? So what are our objectives in this scenario? Yeah, go ahead.
What prevents the second agent from duplicating the data and this?
Okay, so do you mean that
Increase your S2 very vacuously.
but that will not impact. So we are assuming that this accuracy function is not getting improved. Yeah, so it's not, yeah, so it's dependent on the cardinality, but you can imagine that this loss function, I mean, this accuracy function is appropriately chosen. Yeah, so there's data duplication. For this example, it's not the right way of modeling it. But what we are saying is that if I duplicate data, it is not actually increasing the large. Yeah, it's not increasing your cost. It's not also improving my accuracy. Yeah, so in that particular example, this accuracy model is not the ideal one, but yeah, so you can imagine that this loss function, which is dependent on, let's say, the neural network structure, if you are just duplicating data, you are not learning anything new.
So it doesn't sort of hold for such accuracy, like more general accuracy which are dependent on the, or would it be tough to model it?
Yes, I think, yeah, that's why we want to abstract it in terms of the accuracy function. Yeah, but that's a good question. Okay, so what are our objectives? So we want to incentivize both contribution as well as want to learn this W. So the first question is that can the agents reach an equilibrium by updating their strategies while the center is trying to learn W, and both of them, this W and S vector together, reaches an equilibrium in some sort of an iterative manner. And the second question is the more important question, that if the planner or the center wants to force everyone to contribute completely, can they actually do it? And the answer to both of this is yes. So the first answer, which we'll be describing in a minute, is through a best response dynamics. We'll give the algorithm and we'll try to analyze that. The second one is yes, but with certain instrument called payments. So we can actually say, so the long story short, if you want to take something out of this this talk, is that we can actually incentivize everyone to contribute all their data, but we also need to incentivize people who are larger data owners. So for the large hospitals, they should be paid, while the smaller data owners, they will be data consumers. So they will be to this agent, and overall the system will be budget balanced. So that is an interesting thing, that you can actually ensure no additional payment, no additional budget is required from outside. You can just redistribute their money such that the people who have less amount of data, they contribute all their data and also pay some amount of money. The larger hospitals, larger data owners, they contribute their data and use that data as their currency and get paid from the system. And that will solve all these problems. We learn the correct W, we ensure everybody is contributing all their data. Okay, so let's look at the answer to question 1 first. Yeah, so I mean, we just want to show that this is not the first time that we are doing this. In fact, one of the motivation was the work by Murhekar and Bhaskar, their paper in URIPS 2023. The difference that we have brought in is this simultaneous learning as well as this contribution incentive. All right, so let's get into it. So simultaneous learning and the contribution incentive. So just for the interest of this, so we are going to introduce a notation called ZI, which we are calling an effective cost. So why is it defined in this way? So earlier we showed that the utility is just the accuracy minus the cost. So now we are calling it an effective cost because we can potentially add payments to it, and once we add payments, we can either subsidize some of these agents from their cost that they're incurring, and also sometimes give some money, some sort of a tax. Someone is actually being taxed for their contribution. CI minus P, yeah. So yeah. So we are just assuming that this CI minus PI is so depending on what is the sign of your payment, you are either being subsidized or taxed. I'll come back to that in a minute. While the center, who is sitting in who is actually trying to learn this federated learning model, he is not interested in your effective cost. He is actually interested in how accurately you are learning. So some of the accuracies are drawing a connection with the classical mechanism design model, that AI is like the valuation that you get. So some of the valuation is getting maximized. That's the goal of the center. So center is not looking at your effective costs. Okay. Now the first question that we asked is how we can reach this Nash equilibrium, which is W star comma S star. And the algorithm that we are going to propose, which will be in the next slide. So it starts with some W0 is 0. The center is starting with this. And then two quantities we need to define. So the first is the G function, which is just the vector of all the partial derivatives of the utilities of that agent. So just to give you an intuition that this first quantity will be equal to 0 at an equilibrium, because that agent has no reason now to deviate. So once we get this G vector to be very close to 0, then we know that we have reached an equilibrium. And similarly, when the center is actually reaching this gradient is close to 0. So when both these two things together are close to 0, then we are at a Nash equilibrium. That is exactly what our goal is. Now, how do we achieve this? So we call this an updated parameter-based response dynamic. So essentially, each of these agents, starting from that W0 S0, is trying to update their SIs. So agents are updating their SIs, and the center is updating Ws and sending it back to all the agents. So the algorithm proceeds in the following way. In every round, the center is broadcasting the current WT and ST. And every agent, now it is going to each of these agents, they are independently choosing what is that their SI, which is taking, let's say, one gradient step. So this step here, one gradient step towards their, because this is a gradient ascent step, so it is positive. And then they also calculate, so this algorithm requires them to also calculate the local gradients. That's exactly what happens even in a Fed average. You calculate the derivatives with respect to W, only of your accuracy part, not the cost part, and then send all this SI T plus 1 and DI T plus 1, the derivative as well as your contribution, back to the center. Now the center is actually doing the Fed average at their center, and because we have defined G tilde accordingly, this summation so here we are not normalizing with respect to their data contribution. We are just looking at 1 over n, treating everybody equally. And this method, so we keep on doing it for a certain number of rounds. Let's say capital T. Now this algorithm. Just a cartoon representation of what is actually going on. The center is sending your WTs to these individual hospitals. The hospitals are calculating their ST plus 1s from the previous iteration, and then sending back their gradients. And once they do it, they ensure that it converges under the conditions of concavity. Of course, we need some assumptions on this derivatives of AIs and some of the other parameters. We'll get into that, but before it gets a little too technical, let me just tell you the story, what is happening. The requirements are a little stricter than the previous paper lyrics, because we are also ensuring something more, because we need to ensure that it converges both in terms of W as well as S. Okay, so these are the matrices that we are looking at. So the utility of agent I, double derivative of that is constructing constituting the first matrix, and similarly you can define this with respect to W, and so because this W is a vector, you have different components, how many parameters you want to learn. It's taking that double derivative and taking the average of all of them, and similarly the cross derivatives. Once you have that, the assumptions, the requirements under which this converges is that G and G tilde, these two matrices, are strict negative definite, lambda and lambda tilde. So what does that mean? That is G plus lambda of I is negative semi-definite. That's what it means, that by lambda strict negative definite. It's negative definite, but with a certain amount of bias of lambda, where lambda and lambda tilde are both positive numbers. It's not exactly Hessian, because this UI, you see that this is a function of agent I. So in Hessian, you have one consolidated function which are taking derivatives with respect to two things, then you could have said it. So the first row of this G matrix is all derivatives with respect to utility of agent 1. Second is all utility derivatives of agent 2. So it's technically we cannot call it Hessian, but yes, there is similarity, and we are assuming that this matrix should have this kind of a property.
Not even cast it as like a strict concavity.
So we do not know exactly if you can. Yeah, if it was a Hessian matrix, then you could have said that it's a concave function. This utility is a concave. Right, lambda strictly concave, but here we can't say that. And we also need this matrices to be having a bounded norm, bounded operator norm in this case. So under these assumptions, we can show that this mechanism that we just said, that this base response dynamics actually converges to a Nash equilibrium. That is your, so saying it more technically, if you give me any epsilon for every initial value of W0 and S0, we can ensure after a certain number of rounds, where the number of rounds definitely depends on your epsilon, W0 is 0, all these parameters. You can, so remember G was the derivative of your utility. So if it is small enough, and also G tilde was the derivative with respect to W, if that is also small enough, we have reached an equilibrium. So this is essentially that convergence result. You can converge in both these parameters together. Yeah, so this is just the details of that. You will have to choose the learning rates, lambda and eta appropriately, and T0 has to be, so I have just compressed it because otherwise the equation looks a little ugly. But yeah, you can see that this T0 is actually inversely dependent on epsilon. So the higher accuracy you need to run the algorithm for a longer period of time. Okay, so that's this. So it is doing this, but still it is not ideal. Why is that? Because the ideal federated learning model is where everybody is contributing to the full extent, right? So S max is what our objective is. And what we actually want to know or want to learn is this W opt, which is maximizing the sum of these accuracies when everybody is contributing the full amount of data. So this W star and S star that we have just found, that might be far from it. And that is exactly the example that, let me just quickly go to that example to show that you can actually reach a Nash equilibrium, which is very suboptimal, not very suboptimal. So we are going to define this going by the definition of the terminology of social choice. We are going to call this sum of these accuracy functions as the social welfare. Now, this is the example, a very similar setup. Both the agents have a data of 5, size 5. The equilibrium turns out to be that the first agent is not contributing the data at all. The second agent is contributing full amount of data. And if you look at the social welfare, the W star will be 0.5, 1.5, where the social welfare is 1.8. While the ideal situation, so this is the equilibrium social welfare, but if they contribute their data, then the social welfare will be equal to 2. So we are actually losing out if we just let this system flow on its own, and we will not be able to learn any useful parameter. The W opt that we want is 1,2, but we are learning something like 0.5, 1.5. So how can we actually mitigate this issue? Introduce payments. That's exactly the goal. And now we are actually getting into that optimal learning with payments. So now that effective cost is essentially, once we have introduced payments, is the cost minus the payment. So now the interpretation is that if your payment is positive, that means you are actually alleviating the cost to the agent. So that is being subsidized. The agent is being subsidized with this payment. Or it can, if it is negative, that means you are not only its cost plus some additional amount of payment you are charging that agent, which is being taxed, right? So yeah, so you can imagine that agents who have very low contribution in terms of SI, we have a simulation result at the end. So people who are contributing very less amount of data, they will be actually taxed. So they will be data consumers, and the agents who are contributing a lot of data, they will be getting paid. So they will be subsidized. Okay, so we need some mild assumptions on boundedness of this accuracy functions, but they are not that strict. So the payment is essentially a function which looks like this. This has similarities with this DGVA mechanism, if you are familiar with that. But one of the interesting things is beta is a constant that you can choose as a designer. And the important part is this payment is budget balanced. If you sum all the payments, it will automatically be 0. So what it is actually trying to do is that how much is your data contribution corresponding to the average among the rest of the agents. So if you are actually contributing a lot of data, then you will be getting paid. While if you are someone who has very little data contribution, far away from the rest of the agents, then you will be asked to pay. That's the intuition. It does not depend on the cost. Yeah, because we are only interested in the payment being. Yeah, so the payment is only budget balanced among these agents. Right? Yeah.
Sorry, I mean, that's a little weird, right? Because I mean, the payment is there in order to compensate for the cost.
Right.
Large quantity of good data, incurring a lot of cost, and if you want to incentivize them to share data.
Yeah, so I think one can actually do even the cost version, but then we need some assumptions. So the thing that we can show the convergence. So maybe the parameter beta in that case will be slightly different. I think the payment can also be used as the C of SI minus the cost of everybody else. Yeah, so yeah, I think the results won't change, just we'll need some assumptions on the cost function as well. Yeah, so because we are only showing some convergence guarantees, nothing more than that. Okay, so the mechanism changes slightly, the same mechanism, but it is now split into two phases. That's why it's called two-phase. How much time do I have? 7-8 minutes. Okay, fine. So in the first phase, we are just setting a specific W0. A specific W0. We are not updating the W parameters at all. We are just allowing agents to. So with this payment, additional payment, we are actually forcing these agents to go towards S max. So that's how we'll be choosing these beta parameters appropriately, such that that happens. And so after the phase 1, when we reach that S max, then the phase 2 is just Fed average. We are just running at that S max. Agents are all contributing their data, and we are just calculating their derivatives and sending it to the center, and it is trying to learn that W. So putting everything together, so the appropriate choice of beta. So now this beta is determining how much payment that you make. And the intuition of this beta is that you are looking at that n parameter, which was the lower bound of the derivative of your accuracy. And also you are looking at the derivative of your cost. You are compensating by your payment so that you still have so the agents who are currently contributing smaller than SI max, they should be incentivized to actually go towards S max in round 1, in phase 1. And yeah, so that's the phase 2, as you can see, is just Fed average. Once S max is reached, then you are actually going towards that W opt. So so of course we need some assumptions like CI to be convex and differentiable, but still some of these assumptions can actually be relaxed. As long as it has bounded derivative, we should be able to still pull off this. And also for a better convergence guarantee, we need some assumptions on that utility function or the welfare function, which is Kell smooth and mu strictly convex. Not so much important for this talk, but so it is just assuming that the function has some smoothness properties and convex properties. So once we have that, the result is saying that we consider the payment with beta to be at least larger than that parameter. So beta is in our control. We can decide that to dictate the payment. And then your two-phase best response dynamics algorithm will converge to the Nash equilibrium, which is the desired Nash equilibrium, which is contributing the whole amount of data as well as you are converging to this W opt. Remember, W opt was the maximum of this sum of the accuracy, where S max was the contribution. So everybody, that's the ideal federated learning setup, that if everybody was contributing their whole data, what is the W that we learn? That is W opt, and we are actually forcing that this is going to be the Nash equilibrium. And we are also ensuring that the payments are budget balanced, so nobody is getting paid. So somebody is getting paid and somebody is contributing to that payment. But overall, the mechanism designer has neither any deficit or any surplus. Yeah, so this is just the technical details. Don't have to look at it. Just to show that, yeah. So just to show that this T0, the time up to which you need to run this is exactly the same as the log of 1 over epsilon. So the convergence guarantee is still the same. We need some more assumptions, of course, but we can ensure that you converge to the desired equilibrium, which is W opt S max. So yeah, let me just, in the interest of time, skip this. So there are some, for phase 1 and phase 2, there are some intuitions that we can draw from this, but we can discuss about this offline. So let me just show you one example, a simulation result. So you can see on the x-axis how much data each of these individuals contribute, and this is actually using some real data set. So as agents contribute more and more data, you see the green curve, which is the payment. They get paid because they are data contributors, they get paid. And negative green bars mean that they are actually contributing, so they are taxed, so they are data consumers. So they in order to learn the same model, they will have to be paying a large amount of money, even though their utilities are still positive. Okay, so that's the two-phase best response dynamics. So just to summarize what we have just seen, that we proposed the first algorithm, which is updated parameter based response dynamics, that converges to the Nash equilibrium and simultaneously learning the parameter W as well as converging to some S, but that S might not be the nicest S or the desired S, and therefore the W that we learn is far from W opt. Now we update that algorithm into two-phase upgrade, and yeah, so that ensures full contribution from these agents, and that will converge to W opt. So the trade-off is you are using monetary transfer. The transfers are only internal. So an immediate future work would be to consider a maximum budget. Here we are assuming that beta could be any arbitrary. I mean, of course, with those numbers, we can choose any beta. So that means I can actually charge a lot of money to the people who are data consumers and pay that large amount of money to the data contributors. But well, that's zero. But if the agents had a finite budget, then how should we actually adjust that? And also in realistic scenarios, we assume that the data distribution is immutable, but there could be multiple distributions. So somebody is running a hospital in the western part of the country. The disease models are different than in the southern part or the eastern part of the country. In those kind of distributions, maybe we'll try to cluster them into 3 different parts and learn those models, how we can extend that. Okay, so let me just stop at that point. Thanks.
Any questions?
So I mean, just a few details. But is it possible to ensure that the mechanism is at least individually rational, that the payment for an agent is bounded by the utility?
Yeah, that
Have such guarantees?
Yeah, so this is not ensuring that. I mean, of course, in that example, you saw that these agents have individual rationality, but that we have chosen the accuracy function in a specific way. If the accuracy functions are not, so it is not highly rewarding, then maybe you are asking them to pay a lot of money, which is eventually negative. So individual rationality is not guaranteed under this mechanism.
Do results simplify if you consider like correlated equilibrium instead of Nash?
Right. But then okay. You know, so we have not thought about it. But in that correlated equilibrium, we'll have to propose some sort of a, yeah. Yeah, it's
The center can also propose like a
Yeah.
Yeah, so I consolidated a policy for all these agents and they should not be deviating
Okay,
from.
yeah.
Yeah.
Center can act as a coordinating mechanism.
Right, yeah. Yeah. And also, I have seen some of the papers which consider this problem as a cooperative game. So that could also be a interesting stuff, particularly when we look at this multimodal distributions, maybe we want multiple clusters, multiple coalitions to form, and they will be self-sustaining. Yeah, that will be a good direction.
And even core, like you don't
Yeah,
want
core.
hospitals to do like
Right,
opt out. Yeah.
right, yeah.
And so the assumption also is that this S-max is known, is it?
Yeah, S max is known. Yeah, that is the assumption that we are making.
So I have more of a machine learning question than a game theory question.
Hmm.
So at the very beginning of your presentation, you mentioned this like loss function being sort of a sum of individual data points and
Yeah.
just contributing gradients and such.
Yeah.
But there is a very prominent class of loss functions which is non-decomposable loss functions like F measure or some combinations of precision, recall, etc.
Yeah.
In that case, how do you aggregate the gradients in the predicate learning?
If I understand your question, so what do you mean by that specific type of loss function?
So you can't create a loss function as the sum of loss and individual data points. There are some certain loss functions where you cannot do that. Like ranking applications like F measure and such.
Right, but I think in that setup, even Fed average will not work appropriately because you are essentially partitioning. So your data, you are training something on this data and we are adding that learning or the gradients from here to there. So I think, yeah, so an implicit assumption is that wherever Fed average is working, we should be able to use this kind of a incentivizing setup. Yeah. Yeah, I don't know if even so if the data is partitioned and you're saying that the loss function is not additive in that sense, then maybe the Fed average will also perform poorly, and so is our algorithm.
Yeah, thank you.
Yeah.
Last question. Okay, so thanks, Swaprava. Rate of convergence, how does it change? Like for the average to this kind of.
So I think this here we need this epsilon. So
Okay.
something is rate. So
Yeah.
how many number of times you need to
Yeah.
run it depends on what epsilon is.
Okay.
And that will be much faster in Fed average. We
Yeah.
have experimentally verified that.
Yeah.
Of course, we are guaranteeing a lot more, so our guarantee is worse. And if you are just comparing between that without payment and with payment, then that epsilon for that we need this additional
Yeah,
assumptions.
Okay.
It's a pointer I point here or anyway.
It actually is a cursor on this. It doesn't matter where you.
I see.
It's not a laser pointer.
Okay. Oops, how do I? No.
Okay, so our last talk of the day will be by Bhaskar Chaudhary, who's a faculty at UIUC. He has done some path-breaking work at in discrete Fourier division, in particular on the EFX conjecture. But today we'll talk about theoretical foundations of data exchange economies. Over to you, Bhaskar.
Thank you, Siddharth, for the kind introduction, and also thank you for agreeing to switch sessions on such short notice. Yeah, I would like to say that it's an honor to speak here, and I mean, so far the reception has been very warm, so yeah, I'm very glad to be here. So today I'm going to be talking about some of the more recent work that I've been interested in, and like would be, I mean, although it might seem pretty, like that's what that said, that it looks pretty different from like the classic Fourier division literature, but we would see that there is still a lot of social choice questions that we can actually place in data economies. I mean, so the main takeaway is that if like a significant fraction of the people here find interest in the questions at the intersection of social choice and data economics, I mean, I would consider this talk a success. Also, I mean, like as this talk will progress, I would first introduce what are like data exchange economies, what is the desiderata that we are aiming for, and then I would get into the theoretical foundations. So I would encourage you to like stop me at any point, like while I introduce the economy or when I introduce the Desiderata for questions. I'll try to answer them as much as possible. Okay, so without further ado, let's get started. So this is joint work with Hannah from MPI and Jugal and Aniket from UIUC. So I think it's pretty clear that in today's digital world, data is probably the most valuable asset with the explosion of data-driven decision-making processes in almost every sector, like supply chain, healthcare, retail, banking, finance, and many more. In fact, the big data market in the United States is like human research estimates this market to have a global value of $473.6 billion US by 2030. That is like growing at a compounding annual growth rate of 12.7%. So in other words, I mean, the main message is that like data is perhaps the most like it is a very important asset today. And it is high time that we actually design principled economic frameworks that facilitate like any economic process with data. I mean, here I'm just saying sharing, exchanging, and so on, but generally speaking, economic processes with data. And also, I mean, I would like to say that like I'm not the first person to actually consider this direction. So this has been pretty much a very prominent direction in econ-CS community, and there has been a substantial amount of work done. And I will just give you a little bit of taste of what has already been done. This again is not really a representation of the vast volume of work, but just a small sample. So one such data economy is what we call a data market. So similar to, say, the talks we have had so far, where we have buyers and sellers who come to a market with some budgets and they want to buy goods. I mean, the only difference is that you can interpret data here as a good. So what is the unique aspect of data as a good? We'll come to that in a while. Anyway, so data markets are real-time two-sided markets which have buyers. So think of these buyers as machine learning companies who want to buy data for like training their machine learning tasks. And there are data hosted for sale. Okay, so there are buyers and sellers. And this is again a small fraction of the results, not at all representative of the vast literature. I mean, the main message I want to give is that this is a topic which is of interest in like various communities, like we have the econ-CS community, the machine learning community, and also the econ community. So I will just say a few words about some related work on data markets. So it can be like the foundational work on data market or digital goods, which behave in some sense similarly to data, can be traced back to Vazirani and Jain. And Kleinberg and Paislame and Bergman, Bonatti, and Schmolin actually talk about a revenue maximization strategies of a monopolist data seller who wants to sell his data set to like a heterogeneous set of buyers. To the best of my knowledge, Agarwal, Dale, and Sarkar were the first to introduce like an online, like to introduce a model of an online data market where you have multiple buyers and multiple sellers. And this market involves pricing the data appropriately, collecting revenue from the buyers, and fairly distributing this revenue among the data sellers. Since then, there has been a lot of active interest. Say, of late, so there's a paper by Hossein and Chen that talk about data markets in presence of externalities. So that's like a mouthful on data markets without saying anything concrete. But today, we won't be concerning ourselves with this economy. We'll be concerning ourselves with another economy, which is also fundamental and also popular of the classic exchange economy. So we'll be talking about data exchange economies. So data exchange economies, we have a group of agents who have some initial endowments of data. And these agents want to exchange data amongst themselves for mutual benefit. Now, there is no money involved in this type of data. So as a running use case, you can think of as hospital systems or university systems that would like to, say, improve, say, their internal machine learning prediction tasks using data sets from, say, like hospitals or universities, but they're not allowed to sell the patient data or staff data or student data for money. Okay, so there will be no money involved, but there would be, this you can kind of say for most nonprofits, but there would still be principles governing the exchange. I mean, all of this is vague. I will get precise in some time. So, yeah. So before I delve into data exchange economies, I mean, as I promised earlier, I think we need to understand what makes data different from classic assets or classic goods. All right, so I mean, we already have like markets for classic goods. We already have exchange markets that have been extensively studied. So why, like, things with data should be different. Again, I can say a lot of things. A lot of differences are there, but throughout the talk, I will focus on two differences. I mean, rather one difference that is there on this slide currently, and another difference I would make it like towards the end of the talk. So that's kind of to inspire some more future work. But the purpose of this talk, we would kind of stick to this major distinction. So the major distinction being that data is a non-rivalrous asset, meaning that the consumption of data by one agent is not going to affect the supply of this data for other agents. Okay? So in a classic commodity market, like if you have one apple, you cannot have, say, two sellers leaving the market with two apples because there's a hard supply constraint of one apple. But if you have one data set which can be duplicated at zero marginal cost, you can have all the sellers leaving the market with a copy of this data set. And all the market-based mechanisms like the Fisher markets, the exchange markets that we know, like the fundamental concept of policy operates like the competitive pricing rule, the competitive equilibrium, kind of like determines the prices based on demand and supply, which becomes unnatural in economies with data because because it's a non-rivalrous asset. In some sense, we do not have a finite supply constraint. Okay. All right, so if we don't go through the competitive rule, then what exactly are we seeking? So the competitive, so while the concept of a competitive equilibrium does not seem natural to generalize, what we can think of is to generalize the welfare and fairness guarantees of a competitive equilibrium. Okay? So in its most generality, a competitive equilibrium in an exchange economy satisfies the following two welfare guarantees, fairness and welfare guarantees. It's just that these fairness and welfare guarantees are expressed in terms of the competitive prices, and we may not do that for our economy, but at least we want to imitate the fairness and efficiency of fairness and welfare guarantees in its most generality. So the fairness guarantee that we would be seeking is that of reciprocity. So agents that provide good quality data should not be compensated with bad quality data in return. Okay? So kind of similar to the previous talk, where then but it's kind of related to the free riding problem in some sense. This is actually satisfied by a competitive equilibrium. It's just that this condition is expressed in terms of the competitive prices. The second guarantee, which is a gold standard guarantee for any cooperative economies, is that of stability, where we say that no group of agents should have an incentive to break out from the grand exchange and perform an exchange within themselves that they all strictly prefer. So no group of agents should be able to identify a better exchange within themselves. Okay, so these are the two guarantees at a very high level that we will be seeking. Okay, so now I will get formal. All right, so formally speaking, we have n agents. So think of agent I owning data set Zi. And the agents have monotone continuous utility functions. Okay, so those utility functions capture the value that an agent has for any data bundle that can be allocated to this agent. So unless I specify otherwise, do not make any assumptions other than monotonicity and continuity on the utility functions throughout this talk. Okay? And ideally, an exchange is represented by X, where Xij is the fraction of the data set that agent I shares with agent J. All right? So as an input to the utility function, so when I say the utility function assigns the value to a data bundle, a data bundle is essentially this vector. So X1i, X2i, Xni. So the utility that the agent gets from the exchange is a function of the data it receives from all the agents participating in the exchange. You can assume that you can assume that an agent shares all of its data with itself. So its data is there anyways. So since the previous talk was on federated learning, I would just take a second to contrast the major difference between a data exchange economy and federated learning. So in federated learning, it's like that all of you are learning the same, like all the agents are learning the same model. Okay, same machine learning model. Here, it's like an exchange being performed where each agent can learn a private model based on the data that it has acquired from the exchange. So the distinction is kind of a distinction between a public learning and a private learning. Okay, that's the difference.
It depends on the fraction of GI. There's no, it's homogeneous in that sense.
No, I mean, it's not like the utility functions are not homogeneous utility.
Think it, it's not which part of CI exists.
Yes, yes, the data I am assuming is homogeneous here. Yes, you're right. Or otherwise, you can also like you can fix an order among the data points and can have a utility function. I mean, because the assumptions are very, because I'm not putting any concavity sort of assumption there yet, but yeah.
Quality, the quality.
The quality comes from the utility. So like if your data is very good quality, then it should give very high utility to most agents. That's roughly what I mean by what I would mean. We'll see in a slide. Okay, so
Some of these is not bounded by all of them can be one.
yes, but there is no supply constraint. There is no constraint like summation xij equals 1 over I. Yeah, that constraint becomes unnatural. Yes, that's the distinction. Yeah, so there is no allocation sort of constraint, any sort. Okay, so now coming back, so what exactly I mean by, yeah, one more question?
Is shared between many people or allocated to many people, its quality goes down.
I mean, the agents, so yeah, so, okay, so that's, so the short answer is that no, the quality doesn't go down. More detailed answer is that although this is an abstraction, so when I say that data is actually being shared, you don't need to think of it as actually being shared, because in the previous talk, you can have a learning like between, say, a group of agents, where these agents basically report their gradients on this much fraction of their data. So that can be avoided, but yeah, great question. Okay, so coming back, so let's formalize the Swaprava. So this is the slide that I tell you about what we are seeking. And after this, I'll get into more technical details. So if anything's unclear, I would encourage you to ask as many questions here. Okay? All right. So the Swaprava fitness that we call reciprocity. So we say that agents giving good quality data should get good quality data in return. So this essentially boils down to the following fact that every agent's utility equals their contribution to the utility of the other agents. This is how we model it. So obviously, I'm being vague about what I mean by the contribution of an agent's data to other agents' utility. So as of now, I'll explain this in a second. Let's assume that we have a contribution measuring function, psi_ij. So psi_ij measures agent i's contribution in J's utility, in agent J's utility. Okay. Let's say that we have a function that can measure this. So there are these standard functions like Shapley shares that are used in machine learning to measure like data quality. So we can think of psi_ij as something else of that sort. So reciprocity means that the utility that agent I gets, ui of xi, should be equal to the sum of the contributions of this agent in all other agents' utility. You can replace the quantity with a greater than equals to, and the properties of the share function that I'm going to enlist right now, all the results will still go through. Yeah. No. Sorry?
So how do we determine, so it is dependent on the subset?
Yeah, it is, the psi_ij is very non-trivial. Like, for instance, if an agent gets, say, identical data from both agents, then, it's not additive. So, like, the contribution could be different. The contribution may not be equal to the utility. It might be half the utility if there are two agents contributing. So, psi_ij is a highly non-trivial function. So that's what makes the problem non-trivial. Okay, so if there are no questions about reciprocity, I'm going to say a few words about this contribution function then. Okay, so throughout the talk, these are the three properties about the contribution function that I'm going to assume, and these would be satisfied by most popular share functions. The first property is that this is monotone in xij is monotone in xij. So the more data you contribute, your contribution should be higher. And the second is normalization, which says that if you don't contribute anything, then your contribution should be 0. And the third property is that it's indeed a credit sharing function. Like it's what we call the efficiency property in cooperative economics, that summation of psi ij over I should be equal to uj of xj. So if psi ij is measuring the credit of agent I in agent j's utility, then the sum of the credits of all agents should be equal to the utility of agent j. Okay? So these are the three properties that we assume for our share function and nothing more. And just to give you a small, idea that this psi ij can be non-trivial. So consider an exchange with the psi ij may not be separable is what I'm trying to say. So consider an exchange with three agents. So and consider the following utility profile. So the first agent is getting so the first agent gets a utility of 1 if it gets all of agent 2's data, and if it gets all of agent 3's data. And agent 1 gets a utility of 2 if it gets all of agent 2's data and all of agent 3's data. So in this case, you can see, like if you use something like a Shapley share, I mean, just think of a reasonable credit sharing function, you would see that the contribution of agent 2 towards one's utility is 1 irrespective of whether agent 3 gives one its entire data or not, if you use something like a Shapley share. However, if you change this utility to 1, meaning that both these data sets are identical, okay, so there is no extra profit that you're getting data set from both the agents, then the contribution of agent 2 is 1 if agent 1 doesn't receive any data from agent 3, and it's 0.5 if agent 2 receives all the data from agent 3. So important thing is that the contribution of an agent towards another agent's utility does not only depend on how much data this agent gives, but on what data the agent J receives from the other agents. So this non-separability is the main reason behind the non-triviality of the problem that we would see.
This involves also xi and x minus I, right? I mean, it's the entire data vector on which your utility is calculated, right? Because otherwise,
xi is basically the vector. So xi is x1i, x2i up to xni. That's a notation. X is the whole thing. So you can replace the x as x minus, like as xj if you want.
Yes,
so that's the incoming data bundle to agent j. So if you want to be a little bit more precise.
Yeah, so the x is essentially the entire.
Is the entire exchange.
Entire exchange.
Yeah.
It's the entire matrix if you want to.
It's the entire matrix.
The utility is also a function of the entire matrix.
Yeah, I mean, but I was just using xi to say that it only depends on the data you get and not on, like, for the data that you don't get, you don't have, like, it's not going to affect your utility. Size, like if the size is self-continuous. Yeah. Okay, so the second desiderata, so this is pretty much, I guess, standard. So cost-stability says that there exists no correlation of agents and no exchange in this set, such that every agent prefers the exchange, like there's no exchange Y among these set of agents, such that every agent in S prefers exchange Y to exchange X. Okay? So, yeah. Essentially, if this happens, it means that agents in S has an incentive to break free and form a coalition within themselves. All right, so I'll just illustrate with a small example, and then I'll also point out to a subtlety in the definition of co-stability, which is important. So consider a toy example where the utilities agent 1 gets is half of the data it gets from agent 2, and utility that agent 2 gets is essentially the data that it gets from agent 1. So notice that it's very easy to get an only reciprocal exchange, right? It's always trivial. Nobody shares anything. It's trivially reciprocal. And similarly, it is very trivial to get an only co-stable exchange. Everybody shares everything. Because you cannot identify, because of the monotonicity of the utility functions, there cannot be any other exchange which any agent would prefer to this exchange. Okay? So what we are aiming for is an exchange which satisfies both these properties simultaneously. And I would like to point out to a small subtlety in the definition of core stability. So this is subtle, but it also gives us somewhat guarantee on economic efficiency. So notice that we do not impose any conditions on the deviating exchange. So when I require my grand exchange to be reciprocal, I do not impose any such restrictions on the deviating exchange. I don't say that agents at S need to identify a reciprocal exchange which they strictly prefer. They can identify any exchange. In particular, they can identify an exchange where all of them exchange everything amongst themselves. Okay? So this also gives us the guarantees of weak Pareto optimality. Because then we cannot have an exchange which all the agents strictly prefer to the current exchange. Then it's not going to be core stable. Okay? So this is the basically at a very high level. So we are seeking an exchange which is reciprocal and core stable. So if there are any questions here, I can take it. Yeah.
It's right that I just share a part of it and then that's possible. You don't know.
Yeah. So Xij is basically what fraction of it is sharing. You can move away from this model also. So I will talk about an independent work. So you can interpret this Xij as also as probabilities. Okay, and then you can have like expectation formulation of these guarantees, and still the results will go through.
Strict inequality is required because
You cannot, otherwise you will not be able to beat the exchange where everyone shares everything. Yeah, that's why it's precisely required. Yeah. Yes, so it means very good. Yeah, so it means that there is always going to be one guy who's getting all the data from the system, and rather, if you look at any subset of agents, there'll be one agent who gets the entire data from everyone in this subset. So yeah, that's kind of what we are heading towards. Yeah, and still we can guarantee reciprocity. So that's yeah. Okay, so sorry.
Then it would depend on strict monotonicity of functions.
What would depend on the strict monotonicity?
It may not necessarily get all the data, but it needs to get all meaningful data.
Yeah, it needs to get all meaningful data. But like the thing is that if you want to give general guarantees, you can consider cases where SIJs are like the UIs are strictly monotone, and then you will never be able to get any guarantees here. Okay, so there would be, so we can also talk about notions of approximate reciprocity and approximate core stability, which you obtain by adding an additive approximation factor on the right-hand side of the equality and inequality. And it's just for analysis sake. I mean, this is will be pretty much straightforward. Okay, so the problem statement formally is that we're given a set of agents. Each agent has a data set and it's equipped with a utility function. Does there exist an exchange which is reciprocal and core stable? All right. So with the interest of time, so I plan to show you one instance where this is easy to find, but in the interest of time, I'm going to skip through that very quickly. So when
this sticky generalizes the edgewise side or the arrow degree model.
Not necessarily, right? I mean, this doesn't like, yeah, I mean, the reciprocity guarantee is different. It's a parallel of the arrow degree. Like arrow degree goes through reciprocity through the competitive prices, right? Every agent maximizes their utility subject to a bundle. Like if your bundle is more worth, it has higher price, then you have more freedom with maximizing your utility. So they are not comparable in some sense. The core stability guarantee is the same across both the models. Yeah. Okay, so
Marketing they are core stable.
yeah.
This you have to
There also, and like so in that definition of core stability, there is this allocation constraint is inherent, right? So there is the allocation also, like you're looking at exchanges where summation Xij over I equals 1. So that is also not allowed here. So yeah. Okay, so this is a case. I mean, I guess some of you might already be convinced that if you have separability of the utility functions, basically meaning that if the contribution of an agent towards another agent's utility only depends on how much data this agent gives the other agent, we're an easy case to answer. Okay, so I'm not going to go through the algorithm here. I mean, that I had to tell you. So the non-trivial case is the non-separability. Okay, so when my contribution to you depends on what other people's contribution is. All right, so the main results of this talk is that, like, under the general assumptions, that we can show that there always exists an exchange which is reciprocal and co-stable. And the second result is a computational result where we need some more assumptions. In particular, like if you assume, say, bounded gradients for the utility functions and what we call cross-monotone shares. So I'm not going to get into the details of cross-monotone shares, but think of it as you have subordinate utility functions and you're using Shapley shares, then the share function is going to satisfy cross-monotonicity. In that case, we give a local search algorithm to compute an approximate reciprocal and approximate co-stable exchange. So this puts the problem in the complexity class CLS. So it's the complexity of gradient descent. And this, I would like to say that, although this is a remark, it's not surprising. It's kind of contrast to the classic equilibrium, because in the classic equilibrium, the first result, you need more assumptions on the utility functions like concavity. And for the second result, with slightly more general, like if you have, say, SPLC, like even like linear cap, the problem suddenly becomes pretty hard. Okay, so again, so that's a different guarantee, perhaps a stronger guarantee that you're seeking in some sense, but this is a contrast, okay? That I would like to emphasize. So for today, I will just focus on the existence very quickly with whatever time I have left. And the existence will already give you the direction for the algorithm. I mean, it just needs to work out a lot of other details. So I'd like to say that there is also an independent work, which will exchange via utility balancing by Bhaskara, Golapudi, in Polias, and Govind, who's here. So, yeah, I mean, I'll just quickly say that there are some differences, like some differences. Like first thing is that they also focus on another problem in their paper, which is welfare maximization subject to reciprocity. So we're looking at core stability with reciprocity. Then they will look at that too, and also welfare maximization subject to reciprocity. Two differences, but two important differences that I would like to say is that the utility and the share functions in their paper would have a specific form. And the most crucial is that in the definition of core stability, we require the deviating coefficients to be reciprocal. So this is not required by us. Okay, so that's another difference that I'd like to highlight. And in the model, we show the existence of approximate core stable and reciprocal exchanges, and also an approximation algorithm for welfare maximization subject to reciprocity. But it also has a hardness result and an approximation algorithm. Okay, so I think I have 15 minutes. Okay, that's good enough. Okay, so we're going to focus on the existence. And for the existence, we are going to use fixed point theorems, which are kind of constructive, but we will see that, I mean, I will tell you that this fixed point formulation will give us some hint for the algorithm. So generally speaking, I mean, a pretty good rule, what is a fixed point function? What's a fixed point theorem? So given a domain B and a function defined on this domain, which maps every point in this domain to another point in the domain, a point is called the fixed point of this function if the function maps this point to itself. And what are fixed point theorems? So fixed point theorems are theorems that give sufficient conditions on the domain and on the function that guarantees the existence of a fixed point. That's the most commonly used fixed point theorem is the Brown's fixed point theorem, which says that if your domain is convex and compact and your function is continuous, then there always exists a fixed point. And fixed point theorems have been used pretty extensively in calculus, like very generally speaking. So we're going to use a fixed point theorem, and we will use something like Brown's fixed point theorem only. We're not going to use something very fancy. So let's take you through like the terms, and perhaps that will finally take you to the successful proof. Okay, so whenever you try to use a fixed point theorem, and you try to get two properties which are independent of each other, one way to do it is that you try to get one property through the domain, and you try to get the other property through the function. So for instance, you can define your domain to be the set of reciprocal exchanges, and you can define a function such that the fixed points of this function corresponds to core stable exchanges. Okay? But the problem is that these domains are not well behaved for the application of fixed points. Okay? So that's what makes this problem difficult. I mean, the psi function can be really designed, and even the set of core stable exchanges can see that it's non-convex. So here's the thought experiment. So the domains are not ideal, but can we identify a non-trivial subset of the domain? So let's say a non-trivial subset of approximate core-stable exchanges that are guaranteed to be convex. So this is the process. If we can do it, then we'll take our fixed point function from there. Okay? Okay. So to this, I'm going to introduce a very simple concept, kind of motivated from the top trading cycles algorithm. And you'll see that this comes very handy. So define what we call a dependency graph. So given any exchange X, we define a dependency graph, and the vertices of this graph correspond to the agents, and there is a direct edge from agent I to J only if Xij is strictly less than 1. If agent I is not giving its data to agent J, then I have a directed edge. The directed edge kind of shows that I can push more data from agent I to J. So that's how you are supposed to interpret it. So the first observation is that if this dx is acyclic, then your exchange is core stable. Okay? It's not very complicated. So why so? So if your dependency graph is acyclic, well, then look at the sources of this graph. So the sources of this graph get data from everyone because they have no incoming edges. So they are not going to be part of any blocking coalition. And then just repeat this argument, taking agents in the topological order. So agents taken at any point in time will be part of any blocking coalition if their predecessors are not part of any blocking coalition. And if you continue this argument, we can show that, yeah, there exist no blocking coalitions. So the given exchange is going to be core stable. All right. So how do we algebraically characterize this exchange? So here's the characterization. So your Xij lies between 0 and 1, and you take any cycle of agents. And you like this cycle are the cycles in the dependency graph. Okay, so just imagine that quick, and you take any cycle of agents. And I want the product of 1 minus Xij's to be equal to 0. Which means that in any cycle, at least one ij for one of the edges, Xij equals 1, and this edge is not present in the dependency graph. So this will ensure algebraic equivalent representation of all exchanges where dx is acyclic. Okay? Well, I mean, this is clear, but still this set doesn't have the desirable properties that we need. So let's try to look at some approximate core stable exchanges. So in particular, we're gonna add some more buffer, a directed edge from J if Xij is strictly less than 1 minus epsilon. Earlier we were having it to be strictly less than 1, now we're gonna have it strictly less than 1 minus epsilon. So there is some buffer. And we can prove that if this graph is acyclic, then you can kind of get approximate core stable guarantees. Later, we use the compactness of the core stable exchanges to argue for the existence of exact core stable exchanges. Okay, so approximate core stable exchanges are fine for now. So here's the new formulation. I'm kind of skipping through that. So instead of having it equal to 0, I'm only having it less than equal to epsilon raised to n, very small epsilon. Okay, so nothing has happened yet, and this set is still. I mean, this set still may not be convex. It has a very nice property that we will see. So what is that? So let's say that I just like take the log and flip the inequality. This is what I get, and I perform a substitution. So I substitute every 1 over 1 minus Xij's by Zij's. Okay, and as Xij varies from 0 to 1, Zij is going to vary from 1 to infinity. And now this is the set that I have. And notice that this set is a convex set. Okay? And there is a one-to-one mapping between every point in this set to every point in dx. And from every point in dx to a core stable exchange. Okay? So although our set was not convex, there is a homeomorphism from that set to a convex set. All right? So we are going to be operating with the set Z. So actually Zij's vary from 1 to infinity, but we are going to place an upper bound of m. It's not going to make a difference. I mean, we're going to choose the m such that it is significantly larger than 1 over epsilon. So just so that we just get compactness. So we have a set which is a convex compact set,
And there is a one-to-one mapping between every point in this set to an approximate course-table exchange. Okay, so this is the stage one, that can you identify a non-trivial like non-trivial class of convex contact course-table exchanges? We have done that. And also notice that Xij and Xij are like there's a one-to-one mapping. So it's monotone and Xij. So when I define the fixed point function, you can interpret Zij as Xij. So if the fixed point function increases Zij, it means it's increasing Xij, or if it's decreasing Zij, it means that it's decreasing Xij. Yes, exactly. Okay, so so the first part is clear. So next part is to define a continuous function such that the fixed points of this function correspond to reciprocity. Okay, so maybe I'll just, we can drink this water, right? Okay. So we define what we call the surplus for every agent. The surplus can be interpreted as a utility outflow minus a utility inflow. The first term, summation over psi ij, indicates how much utility this agent is giving to the exchange. And the second term is how much utility the agent is getting from the exchange. Reciprocal exchange, you need surplus and the agent to be equal to 0. But due to the proper, and I'm going to be writing it as a function of z, not as a function of x, because just as I said, we will interpret z as x. And also by the property of our shared functions, we know that the sum of surpluses is 0. So it suffices to find a point where the surplus of all agents are the same. Okay? So long story short, so we want to find a point z in our convex compact set capital Z, where surpluses of all agents are the same. So let's try to do the most obvious thing, that where the surplus of I is larger than surplus of J, then what is it that we should do? So it means that I is given more and J is given less. So it makes sense to reduce Zij, that is how much I is given to J, or increase Zji, how much J is given to I, right? We will always thing to do. But obviously, this won't be that easy, because if you try to do this on these updates, you might move out of your feasible set. So here's a fix that, okay, let's say that we do it continuously. I mean, I'm going to ask you to believe me at face value that this can be done continuously. Let's say that we do it continuously as long as it is still feasible. Okay, so as long as I can increase or decrease Zij or Zji, I will do it. So now, if you believe me that this can be done, then all I need to show you is that if there is a point where the surpluses are not or equal to 0, there must be some pair of agents, I and J, such that surplus of I is larger than surplus of J, and either reducing Zij or increasing Zji is going to be feasible. And our function is going to do that. So how do I convince you of that? Well, it's a lot of technical slide, so we're tired. So, okay. So let's say you partition the agents into two blocks. The first block of agents have positive surplus and non-negative surplus, so these agents are giving more. And the bottom, these agents are giving less. So by some basic flow-based arguments, you can argue that there will always exist an agent I that sends sufficient flow to agent J. This can be argued. Shouldn't be that difficult. Okay, so the first thing is that is reducing Zij feasible? If it is feasible, we're done. So if it is not feasible, it is not because Zij is close to its lower bound. Because I said that there is sufficient flow that's being sent. Okay, so it means that it's the reason that it's infeasible is not because Zij is 1, or basically Xij is 0. I know that Xij is non-zero and Zij is greater than 1. So the only reason is that if I reduce flow from I to J, it's going to introduce a cycle in my dependency graph, which will make it infeasible. This is the only reason. And if this is the reason, well,
You start with a low surplus agent, and you move along the edges of the dependency graph, and you get to a high surplus agent. Meaning that at some point in time, you would have crossed from a low surplus agent to a high surplus agent. And since you have an edge in the dependency graph, it means that there is slack in this edge. You can increase flow from B to C. Okay, because that's the definition of these edges. So clearly, if reducing from I to J is not feasible, will exist B and C such that surplus of B is less than surplus of C, and increasing ZBC is feasible. So this will, yeah, so this basically shows the existence of reciprocal and co-stable exchange. I think I don't have much time, so I won't get into the details of computational results, so but I'll just tell you the high-level idea. So at a very high level, our algorithm is the same, that it maintains the set of agents with high surpluses and the set of agents with low surpluses. And the exchange is such that the dependency graph is acyclic, so we get core stability for free. And at every point in time, we try to reduce the surpluses of the high surplus agents or increase the surplus of the low surplus agents. So we kind of show that you can make progress on the potential function, which is like the balancing potential function on the surpluses of the agents. So that's roughly what we show. And I wouldn't say more than that. Yeah, I mean, the main challenge is that changing flow on one edge can potentially affect the surplus on all the other edges. So, although I mean, it's pretty much non-trivial to show progress. I mean, you need to really use the submodularity of the utility functions to get this. To summarize, we introduce a formal framework for data exchange economies. We prove the existence of reciprocal and core-stable exchanges under very general conditions, and we outline a local search algorithm to compute an approximate reciprocal and approximate core-stable exchanges under some specific assumptions. All right. So going forward, so two obvious problems in the same framework is that what is the computational complexity of determining an approximate core-stable and approximate reciprocal exchange, very generally speaking. So if you don't make any such assumptions on like submodularity, most likely it is hard, but it's still, I mean, we don't prove any results. So this is open. And also, I believe that another interesting subcase is that arises quite frequently in practice is when agents have complementary data sets. Okay, so this is not covered in our case. When we, like complementary data sets is essentially supermodularity in the utility functions. So for that case, and I feel like that alone is an interesting subcase that at least I would like to know what is the computational complexity, or can even give any algorithmic paradigm for it. So these are many questions you can ask, but these are, say, pretty much like the framework we work with is very general. So yeah, I mean, these are the questions that you get immediately on the framework. Yes, I will promise you that there are differences and challenges that a data economy presents to a classic economy. So here is another major challenge that we do not talk about in this paper. So one thing is that agents have like weak priors on their utilities. So these agents like that seek, these agents are typically these machine learning companies who want to improve the accuracies in their predictive tasks. And usually without using the data and seeing the improvement in performance, they do not have an idea of what their utility is for the data. So how do you surpass this problem? So especially, we approach the assumption that the whole exchange happens through a trusted central server, where the agents can upload their prediction tasks and their data sets, and the server can answer queries regarding what is the value of the data to any particular agent. But obviously, I mean, we would like to have this problem work in a more decentralized setting. And there, I guess the challenge is to surpass the problem that I actually showed. I mean, we primarily with utility functions, maybe some immediate direction can be that you can have, like some agents can give some data samples for free, such that the other agents can build a proxy utility function. So this is an approach that I've seen in some machine learning papers. So essentially, if you were to build on this framework, the exchange will have two parameters: how much data you give to this agent and how much data you give it for free. So maybe things would change, but yeah, maybe there are other ways to do it moving away from this framework. Nevertheless, I feel like there are lots of interesting questions that I mean, the theory community and the social choice community is likely equipped to solve. So I would end my talk here. Thank you.
Some questions, maybe quick ones, and then in the interest of time for further discussions, you can ask her later.
So did you say that the equality and reciprocity could be replaced by inequality as well? Would that and everything works over there, or
Greater than equals to.
greater than equals to? Okay. That the utility should be at least the contribution.
Yes.
I see. Okay.
I mean, yeah, good sessions here. I should ask one. So there are these results like for large economies, you get core convergence kind of results. So if it's enough, so those are.
You're talking about dynamics, like that can lead to.
So there are these results like the Edgeworth conjecture and all that. That if you have enough agents of the same type, replica economies as they are called, then it's core convergence. So you will get core just because there's enough repetition.
Ah, that's an interesting direction. I mean,
So there are two extremes, like very few agents, the constant number of agents would completely complementary, as you said. The other end of the spectrum is you have many agents and take them. I mean, the same data is available with a lot of people.
right. I mean, so this setting that we're discussing with
Yeah.
suborbital utilities captures that
Yeah.
in some sense, right? Like,
Yeah.
because more the data you share, your marginal is not as good, but I guess, algorithmic results or
It's a
like this,
econ result which says that if you have enough similar individuals,
the core exists.
core exists.
Yeah, the core exists. So, okay, so maybe this is, so the core exists anyways, right?
Yeah.
Very generally speaking. So another economy that I didn't talk about here. So, like I talked about reciprocity with core stability, right?
Yeah.
So another thing that you could look at is that as like Swaprava was saying that you can have costs also. You can get, so the whole point of reciprocity is because it goes through a centralized implementation in our case, and a centralized survey is expected to be fair. So it's that, like, it's kind of compensates for the costs. Like if you give good quality data, you're going to get good quality data in return. So you can get rid of the reciprocity altogether, and you can have utilities defined to be accuracy minus costs. And here I know that core does not exist.
Okay.
Okay, so it's not a known result, but we thought about it. So here, for instance, I guess it makes sense to ask questions like perhaps in large economies, what would happen? Like what are sufficient conditions, or what are the natural instances where core exists? But under this, like through parallel, and it's also a natural parallel to the algebra. So here, I feel it exists in very generality.
Okay, let's thank Bhaskar and all the other speakers for the day. I'll see you tomorrow.
Yeah, I mean,